Hey, hello everyone, thank you for coming to this event. Today I'm going to be presenting a new project of mine that I've been working on for the past half a year or so, which is called Wendy OS. Wendy OS is an embedded Linux operating system written based on Yocto. Yocto is a build your own operating system kind of tool, kind of like Buildroot. And we've been using this to build Wendy OS, our new operating system for embedded Swift. So when I mean embedded Swift, I don't really mean the microcontroller embedded Swift. I mean kind of more like server-side Swift. So what is Wendy OS? Wendy OS is your all-in-one package, kind of like iPhone development for Linux devices. We've tried to reduce the amount of steps needed to get your first Linux device up and running, which are these three down below. So first you'll want to brew install some CLI tool, which is our Wendy CLI. And when you have your Wendy CLI, it installs swiftly, it installs the right Swift version, and it installs a cross-compilation SDK, which is based on Swift SDK generator. From there, you can Wendy OS install, which will prompt you with a list of supported hardware devices. And right now we support the NVIDIA Jetson for ML use cases and Raspberry Pi. Finally, you can run your Swift project using Wendy Run. So how does Wendy OS envision to look? So we kind of think that IoT and robotics will be everywhere very soon. We've seen AI take over a lot of the space, but also I think while AI is making it easier for you to develop software with LLMs and things like Claude, I think the hardware space is way behind today. And I think Swift is the perfect language for helping empower this new movement of AI-generated code. Because Swift is able to correct both developers and LLMs when they create code. For example, race conditions, memory safety, and all of the other problems that are plaguing this industry. This is causing not just security issues, but I also think Swift is an excellent. I think also embedded systems are plagued by slow iteration cycles. For example, when you have a microcontroller, updating it is fragile. You make one mistake in your update, people download the binary, and before you know it, nobody can update their microcontrollers anymore because your code is crashing. Swift, of course, helps prevent a lot of those issues just by being a safe language. But the same problem of slow update cycles is prevalent in Linux-based systems too. So let's go through the 4 steps of this presentation. I want to share the goals that we had when designing our tools and OS. Most of our tools are open source or contributed upstream to Swift packages. The architecture we had in mind when we designed the operating system and tools around it. We had some missing pieces in the Swift ecosystem that we needed to fill. And then there are some future directions I'd like to take Swift next. So the goals. We had 3 goals in mind when we wanted to envision a future for embedded systems. We wanted fast iteration cycles, a secure environment for you to play in and update your apps. And finally, we wanted to make sure that we can scale whatever you build for the real world. So we wanted to leverage the existing ecosystem around Swift to make this happen. Not just because we think these tools are critical to development in Swift in general, but also because they're excellent examples of how to scale your code. For example, we wanted to use Swift OTel for observability so that you can remotely monitor your app's success in the real world through the cloud. But also we use OTel in more interesting ways for local debugging too. We leverage Swift Container plugin for packaging your apps, and then we use Containerd for running them. So these are a few of the packages that we've used and contributed to over the course of developing this project. The basic architecture of Wendy OS is kind of similar to regular Docker. You have a command line utility written in Swift using gRPC Swift that runs on macOS, Windows, and Linux. We have an agent on the other side, just like Docker daemon, which exposes a Swift gRPC API using MTLS on your local network, and then using MDNS we allow you to discover your device, and we also broadcast over BLE. We have a container registry on the device, so you can push your Swift container plugin based apps directly to the device. Finally, we have an OTel proxy that takes your Swift OTel telemetry and sends it to either the cloud, some other tool like Sentry, or maybe your local development environment if you set up a debugger there, a debug system there. Finally, we integrate with the rest of the Linux ecosystem, which is heavily based around dbus. If you're unfamiliar, dbus is kind of like an IPC mechanism on your Linux device. Many services like Network Manager or BlueZ communicate through dbus to expose their APIs in a language agnostic manner. And finally, we have a gRPC spec for communicating with a cloud that you can implement by yourself, or you can use our open source solutions for that. So the Wendy agent is the centerpiece of it all. This is where a lot of the magic happens, and it's a gRPC Swift server as I mentioned previously. It also hosts a Hummingbird server, HTTP API, where you can upload your containers. This uses Swift OTel for Swift Open API generator for uploading these HTTP calls. So whenever your Swift container plugin, which is written in Swift, sends the container over, the other side is also Swift receiving the data. We have an OTel proxy that sends the that collects all of the metrics and data from your device and then uploads it to your destination. And like I said, we integrate with BlueZ, so you can discover your device locally over Bluetooth as well. This I mentioned. So to start a container, you run Wendy run. This does a couple CLI requests, like checking if the container layer is already uploaded. So if not, we can skip that. The gRPC agent, the gRPC server on the device receives the call, then sends it to the container containerd, which is kind of the underlying mechanism for Docker as well. This is the runtime that actually runs your container. And then using Swift Neo, we tail the logs from std out and std error, so you can actually see them in OTel if you don't have Swift OTel set up. But I highly recommend using Swift OTel for structured logging and other mechanisms. Okay. Finally, we found it very important that you can remotely debug your application, but on server-side Swift today, you cannot remotely debug your application yet. For this, we had to modify the Swift container plugin, so you can add extra layers and extra binaries. In our case, we use DS2, but you can also use LLDB server to run your app inside of the container environment, and then you can attach to it from VS Code. We have a VS Code extension for Wendy, but we're also trying to upstream this into mainline VS Code, and then you can, and hopefully we'll repeat the same pattern for Android debugging as well. We made a couple PRs for this, including Windows support, and before I continue, I want to demo kind of what the flow looks like and how it works. So over here in the Wendy Agents repository, I have an examples directory with a couple projects. Some of them are GPU-based or Python-based, some of them are Swift code. So to start, let's take our Swift project over here. It's a simple package.swift. I'll make it a bit bigger. So it's a simple package.swift, and if we open the package.swift, you'll see it's in the hello world that you are used to from Swift init, Swift package init. The sources are not very enticing either, it's just the regular hello world, but this is the basic application that you want to try and run. So normally on my Mac I would use Swift run, and it compiles my app and it does hello Wendy. So if we Wendy run it, you'll see that it checks the Swift requirements. This calls into Swiftly to check if the right Swift version is installed before downloading or building the Swift cross-compilation SDK. Finally, it checks if you have Swift container plugin installed as part of your project. If not, it prompts you to install it. And then it builds your Swift app using Swift container plugin, cross-compiles it, and runs it on the device. So now it's uploaded to my device and I see hello Wendy. You might not see this directly, but I have my device connected over USB right now, and that's all that's needed to get started with debugging your Raspberry Pi or developing for Wendy for an NVIDIA Jetson. So let's try something more complex. hello HTTP. Again, we have a simple Swift package with Hummingbird. We can run it. We could even remote debug it with VS Code, and that's the basic flow. Now that you understand how the system is supposed to function at a high level, I want to quickly dive into some details of how we build this on a more technical level. So, like I said, the runtime of most container tools, including Kubernetes, is Containerd. Containerd is a gRPC-based API that is able to extract your container onto the file system before running the executable that you have done in there. Containers are not really virtualized like a VM. They're more like an isolated subsystem, like an isolated component within your Linux distro. What else? So, so to make this work, we had a couple PRs to make to Swift Neo as well, which I'm trying to push further. And we're also looking at expanding the system towards more embedded microcontroller-oriented devices as well, where we're thinking of using WASM to package your application and run it on the microcontroller, so you have a safe area to update. Some other ideas that we're currently working on are building a cross-platform networking library, just like Swift Neo, but that also functions on microcontrollers with Bluetooth support. Finally, we're trying to improve the SDK generation process, so you can create your containers, create an SDK for your container in seconds instead of the current minutes that it takes. Thank you.